So good day everybody. Thank you for joining this presentation and taking your time to have a look at this. These strange times bring us in strange situations, and that gives me ending up here making this video for you from my home office. However, once again, thank you for your time and joining us. My name is Ries Augustijn. I'm from Intero Integrity, and I would like to give you a update on our cost-effective ultrasonic inspection tool for large diameter pipelines. Thank you. So first I would like to give a brief introduction to our company. We're Intero Integrity. We are formerly known as AHEC Industrial Services. We were acquired by a private equity investor about 1.5 years ago. We provide several services for the capital intensive heavy industries, so oil and gas, power and energy. Our services break down into industrial services, which execute several nitrogen cleaning and nitrogen heating and cooling services. We also do decommissioning, leak detection, whatever kinds of things are needed for service activities. We also have an inspection services department, which provide non-destructive testing services, mainly all based on ultrasound technology, either for pipelines, for above ground storage tanks, and for furnaces. And next to that, we recently joined our forces with a company called the Sniffers. They do emission management. They're also present here at PTC, so please take your time to have a look at them as well. Our inspection services are available on a global scale, so we have offices in North America, Middle East, Far East, and obviously Europe. And wherever we don't have offices, we have our local partners being able to supply our services. This presentation focuses on our ILI tools, so we have a vast amount of different inline inspection tools for inline pipeline inspection, all based on ultrasound. Obviously, we provide supplementary services as well, like geomapping and XYZ. Our tools provide solutions for pipelines ranging from 3-inch to 64-inch, so that's quite a large extent of diameter ranges. And we typically focus on what we call the challenging pipelines. So that means that all easily pickable pipelines are mostly not the type of pipes that we tend to inspect. Our tools are bidirectional. We can cope with short radius bends. We can cope with multi-diameter pipes with offtakes, mitered bends. We execute our projects both on and offshore. If required, we can execute pipeline modifications, either temporarily or fixed. So all in all, the challenging pipelines are our challenge, and most of the time we have success in making them pickable and provide you good quality inspection data. So the tool that I'd like to present here focuses on the development of an inline inspection tool. The technology is based on ultrasound. It focuses on metal loss detection. This tool typically is developed for pipelines ranging from 20-inch and up. And the main challenge was that we wanted to have a tool that is flexible for various products, such that we don't need to inspect everything in water, but we can execute the inspection in the product that's put through the pipe, which is a huge operational saver for cost and environmental burdens. So the objective was to develop a small tool, single body, to the extent that you can call a 64-inch tool a small tool, but it is a single body tool with bidirectional capabilities. It would be possible to calibrate the tool on site. And the challenge was to have increased sensitivity, which means that we wanted to be able to have high resolution ultrasound inspection with this tool in various products. And that's mainly what the main challenge was for this development. So starting this project, obviously you set the targets for the project objectives and the requirements, and then you start working from scratch, running some simulations. In this case, we done many simulations in SIVA, which we used for the probe design of the phased array tool. The tool, as I said before, had to perform in various inspection media. Since it's ultrasound, it has to be a fluid, but next to that, we wanted it to be compatible with anything varying from water to diesel and naphtha. So with the SIVA simulations, you use that for calculating the delay loss, for how to fire the elements in the probe, and also to calculate how the beams perform in the different media. So what we try to demonstrate with this slide is the relevance of deploying a properly designed ultrasound concept in the right conditions. On the left hand side, you see here an image which depicts a ultrasound beam in water designed for use in water, and on the top hand side here's where the probe is located, and this is the pipe surface. And what you see is that the energy of the beam is nicely focused, and the high intense energy is perfectly at the pipe surface, and that gives high quality measurements with good signal to noise ratios and highly accurate measurement grid. So what we try to demonstrate here is what would happen if you would use this exact same probe, not in water but in naphtha, and that's what we imaged on the second image. So what you see here is again the same probe, but the product in water, and what you see is that the beam is completely out of focus. The energy is not focused, it's not concentrated in a small spot, and this results in very poor ultrasound data, bad signal to noise ratios, bad sensitivity for small defects. Your measurement will be completely a mess. So in the next 4 pictures we deployed a similar setup, but then with the phased array probe. And the nice thing with the phased array probe is that by just modifying the settings of your electronics, you can define the shape of your ultrasound beam. And that shape can be modified to what kind of material you're inspecting through, so what kind of product is in. It can be modified to what standoff difference you have from the probe to the pipe wall. So that makes it flexible for various products, but also flexible for various pipeline diameters. So in this case, we set the focus point of the settings to very close to the probe itself, so only at 100 millimeters. And you see that the beam is fairly small over there. But if the focus increases, so up to 200, 300, even 400 millimeters, you see that we have a nicely focused beam with high concentration of energy in the center of the beam, exactly where we want to have it. And this gives us the opportunity to tune the shape of the probe based on the type of product that we're inspecting in, and also based on the type of pipeline diameter that we're inspecting in. So that's mainly the main advantage of this system. So once you've designed that, obviously you want to verify if the design meets the reality, and if the design meets the quality criteria. So for that we created a calibration spool. So basically, if you consider a pipeline, there's product in the pipe, which is demonstrated here in the yellow part, and there's a steel pipe wall, which is the black part, and in that pipe wall we created several internal defects but also external defects. And as you see, the defects are all varying a bit. So we created flat bottomed holes, but also hemispherical bottomed holes, both on the internal diameter but also on the outer diameter. And we also changed the size of these holes. So what's happening then, once we run the tool through the pipeline, you will see that there's a huge difference in the reflective area of all these individual types of defects. So normally, you have your beam and it's nicely focused as you want to have it, and it reflects here on the flat piece of pipe. So you get like a mirror, you get a perfect reflection, and you get a very good signal to noise ratio measurement. However, if you move the system through the pipe, you can imagine that in these curved holes you will get some scattering, but since the curve is relatively big, the scattering will be limited, and the signal to noise ratio of the reflected signals will be quite okay. And then if you move on, the signal will go through a deeper hole, so in all the timing of the reflections will be different, and as we all understand basic ultrasound, I assume that it will be clear that you can measure the depth of this defect. However, what happens if the again here on the defect on the outer diameter, you also get reflections from that, and even in the smallest defect in a round bottomed hole, you get some reflections back. What I want to stress here is that there's a huge difference in the amount of energy that's reflected by the beam compared to the size of the hole. So if the hole gets smaller, the amount of energy, and particularly if you have a hemispherical bottomed hole, the amount of energy that's reflected back reduces exponentially. So that's something to take into account when you consider these type of calibration spools. So when you start building this calibration spool, we decided to have it done on a 24-inch pipeline. The spool contained both internal and external defects. We created flat bottomed holes and hemispherical bottomed holes, all diameters ranging from 6 to 28 millimeters, with defect depths from 3.2 to 5.2 millimeters. The original wall thickness of the tool was 9.2 millimeters, and the spool contained 28 artificial defects. The product that we did validations in was crude oil, and altogether we executed 6 scans. And when you look at the POF figure, and you consider the shapes of the defects that we are considering here, it can all be considered either pitting or pinhole type of defects. So the test setup looked like this. So it was a vertical piece of pipe, and the tool was lowered through the pipe to record the data. And in the end, the data looked like this. So it's already quite easily visible all the different kinds of defects that we have in, but we'll go into more detail in that later on. So after analyzing the data, we obviously were interested to learn what the probability of detection is for all these type of defects. And when we consider the flat bottom holes, we can consider them with 100% POD. So all flat bottomed holes were easily identified. And the A1995 for the hemispherical bottom holes was 10.5 millimeters. So that means that with a 90% reliability, we could find hemispherical bottomed holes from a 10.45 millimeter diameter and bigger. Altogether, this data set contained 168 samples. So after establishing the probabilities of detection, we were also curious to learn the sizing accuracy. So when you consider all the detected defects, we analyzed them to see what the sizing accuracy was. So what you see here is the typical sizing accuracy graphs. So on the x-axis you see the actual defect sizes, and on the vertical axis you see all the measured sizes. And the further the dots are apart from the center line, the worse it actually is. So when we look at the measured length and height of the defects, we tend to oversize them a bit. So that means that we call them slightly bigger than they actually are, which is on one hand good because it's a bit conservative. On the other hand, you try to be spot on. So our current idea is that this is part of the analysis procedures and software that we used. So we're further improving on that. However, when we consider the depth sizing accuracy, both for the flat bottomed holes and the hemispherical bottomed holes, we are with a 2 sigma tolerance of 0.2 and 0.1 millimeter, which is obviously the most important characteristic for the remaining pipeline strength and life, and we're quite accurate on that part. So we're happy with that. So now I'd like to tell a bit about our case study. we executed several projects already with this tool, but this case study specifically goes into one project, which was for a tank farm owner, and they have several interconnecting pipelines on their tank farm, and these have the following characteristics. So the pipeline diameter was 28 inch. It had various different types of nominal wall thicknesses, varying from 7.9 to 12.7 meter. There was typically a very short piece of pipe, 110 meters. However, it had to be inspected. So the operational product for the line was crude oil, and we inspected in the same product, which was obviously a big advantage. So the results were gathered in about 1.4 hours. We reported 226 anomalies, of which were 10 metal loss anomalies. We also included the validation spool that we examined in our backyard previously here in the pipe as well. So here you see our validation spool, and that proved for us that we were able to achieve similar results as we did on our mock-up testing. So concluding, the pilot projects that we have executed so far are all quite successful. So we were able to develop a single body bidirectional tool from ranging for pipe diameters from 20 to 64 inch. As I said, the case study that I demonstrated was about 28 inch. We also executed a similar project in 56 inch. So that's significantly larger. The tool has a very small sensor head, as you can see here, which gives us the opportunity to be very flexible. It's basically a bidirectional cleaning pick that we mounted everything on, or at least it has the same form factor. So that gives us the ability to cope with tees and offtakes and short radius bends and reductions. It also allows us to install small pick launchers, which obviously is always a big benefit from an operational perspective. The tool is flexible for various types of liquid products. It can cope with light to heavy crudes. It can cope with naphtha, gasoline and diesel. The tool can be equipped with a fiber optic wire for online performance monitoring and data collection, which obviously has got benefits as well when it comes to quality assurance during the run, but also to be able to give a rapid call on the success of the inspection. The quality of the tool can be guaranteed despite the changing product properties, as we have demonstrated. So that's a good thing. The tool is time efficient because we can inspect in product, which reduces the out of service duration obviously very significantly, and it gives us a swift insight in the success of the inspection run because of the fact that we can transfer the data through a fiber optic wire. So we also demonstrated cost effectiveness. In this case, we were able to run the tool through a 100-meter pipeline, which is obviously very small and has quite considerate mobilization cost. But in this case, all in all, for this customer, it was worthwhile to do this investment and to get the know-how on the pipeline that he wanted to have. And obviously, from an environmental perspective, it's very good to run the tool through the original product in the pipe, because it saves a lot of cleaning and wastewater removal. So that was it. Thank you all for watching. It's a bit unfortunate that I'm not able to answer any questions from this end. However, it was a nice experience to give this presentation to you like this. And if you need to contact me if you have any further inquiries or questions or need to have some clarification, don't hesitate to contact me. It can either be done via the PTC app, but obviously also via my conventional contact information that's here below. So once again, thank you all, and thank you for your time. Bye.